For our fourth installment in chapter 18, we're going to talk all about substituents. In our previous video, we talked about things that are activating and deactivating in those different classes, and we'll see the effects that those have on reactivity in video 4. Because the substituents don't only affect how benzene derivatives react, they can also affect where new substituent goes. If I already have a substituent on benzene, right, the question is, where does the next one attach itself? And the identity of the original substituent, X in this case, that's on there, determines where the new substituent, Y, will go. Okay? Things either direct to the ortho and para position, or they direct to the meta position. Okay? And they're called directors. They're ortho-para directors or meta-directors. Keep in mind that ortho and para are together. Everything that is considered an activating substituent and our halogens, the weakly deactivating substituents, those are all ortho-para directors. Okay, so if I have any one of those substituents, right, so strongly activating, moderately activating, weakly activating, or weakly deactivating, any of those four classes will put the next substituent in the ortho or para position for a reaction that you're doing. Flip side of that, things that are moderately or strongly deactivating will direct substituents to the meta position. And the reason that we have these, right, either ortho-para directors or meta directors, has to do with the stability of the carbocation intermediate that we have in these reactions. Because keep in mind, right, the transition state in these reactions resembles that of the carbocation intermediate because we've got that endergonic first step. So let's look at an ortho-para director. Okay. Here I've got my methoxy substituent that donates electrons by resonance. Okay, so it's activating. This is an ortho or para director, and here you can see why. Looking at putting a substituent in the ortho or the para position for our carbocation intermediate relative to the meta position gives us a fourth additional resonance contributor, right? And the more resonance contributors something has, the more stable resonance contributors anyway, the more stable something is. And these new resonance contributors over here are exceptionally stable because they're the only ones where everybody has a complete octet. So we see that for things that donate electrons by resonance and for things that donate by hyperconjugation. Okay. Now we don't have an additional resonance contributor, but this is where we get our more stable resonance contributors. Notice these are the only situations where I get a tertiary carbocation. Okay. So again, ortho and para director because they're more stable with that intermediate. But if I flip now, okay, and I go to something that's deactivating, right? Notice I've got protonated aniline here, that's strongly deactivating. Okay, now I don't want to put that carbocation in the tertiary position because it's right next door to a positive charge. Right? And way back when we first looked at resonance contributors, when we introduced delocalization, remember you never want like charges next to one another. Okay? So anything that is electron withdrawing and deactivating, except for the halogens, which are weakly, those are meta directors. And they do that to avoid neighboring positive charges. So as you go through when you're studying, are things activating or things deactivating, add in there, are they ortho-para directors or meta directors? Okay. And it's all summarized right here. Everything that's activating plus the halogens, which are weakly deactivating, those four classes are ortho-para directors. Things that are strongly and moderately deactivating are meta directors, so two classes there. And a trick to help you find this, it's kind of a lifesaver, right? Look for the substituent. Okay. If it has a lone pair on the atom that's next to the ring, it's going to be an ortho-para director. You also have alkyl groups, aryl groups, and alkenes that can be ortho-para directors as well, but that's a quick tip to help do it. If the atom that's directly attached to the benzene ring has a positive charge, like we just saw, or a partial positive, it's going to be a meta director. The next logical question, right, is for things that are ortho-para directors, how much of each do you get? what percent ortho, what percent para, right? And it all comes down to the size of the substituent. Because keep in mind, there's two ortho positions. If I take toluene up here, there's an ortho position on the left and ortho position on the right, and there's only one para position. So ortho is more probable, right? But it depends on the size of our substituent because the ortho position is also more sterically crowded. So the larger the size of your substituent that's on benzene, or the larger the size of your electrophile, the greater the chance it's going to favor the para position. But even at the end of the day, if you get two products, they're not difficult to separate because they have different physical properties. So you can separate them out by things like distillation. Not that bad. But no ortho-para directors, no meta-directors, right? Be able to predict how those reactions go. Next thing we're going to look at is how substituents can affect reactivity. Yeah, a quick look back at our original 5 EASR reactions and how they can be affected by substituents that are already present. And then we'll jump right into seeing how that affects synthesis. Okay? Because we said at the beginning, halogenation reactions of benzene require a Lewis acid catalyst. But actually, if we have something that's strongly activating on there, like this methoxy group, and you're just trying to put on one bromine in this case, you actually don't need to use a catalyst and you don't want to. Because you see at the bottom, because of the effect of that activating substituent, if you use a Lewis acid catalyst, you don't get something that's monosubstituted, you get trisubstituted. The strongly activating group is an ortho-para director, and it's going to brominate all of the positions if you use a catalyst. And that's because halogenation is the fastest of our EASR reactions. But the flip side of that, Friedel-Crafts reactions, the alkylation and the acylation, these are the slowest of our 5 EASR reactions. And they actually won't occur if you have a meta-director on there, things that are moderately or strongly deactivating. Even if you use a Lewis acid catalyst, if there's a meta-director on there, it's not going to go. Okay? And in addition, right, aniline, just be aware of this, also can't undergo Friedel-Crafts reactions because the Lewis acid catalyst that you have to use ends up forming a complex, right? The lone pair here acts as a Lewis base that attacks the Lewis acid, right? And then you have a positive charge on nitrogen. Now it's a meta-director. Can't undergo the Friedel-Crafts reaction. One other note to pay attention to, right? Aniline is tricky in terms of its reactivity. You also can't nitrate aniline because nitric acid, and so, right, remember for nitration, you have to use a mixture of nitric acid and sulfuric acid. Nitric acid is an oxidizing agent. It'll oxidize your NH2 group. Okay, so it's a much more involved synthetic procedure if you're trying to nitrate aniline. Right, you first have to acetylate the amino group, and then remove that by, then nitrate, then remove it by an acid catalyzed hydrolysis. So just something to have on your radar, not necessarily to commit to memory. But keep all of these reactions that we just discussed in mind for our synthetic applications, because that's what we're talking about next, looking at putting on 1, 2, or 3 groups onto benzene. All about designing a synthesis. Right? And as we jump through these different synthetic examples, there's 7 of them, right? You can look at them all in depth on your own time to review all of the reactions from this and previous chapters. But the big takeaway, right, is you'll appreciate the difficulty of being a synthetic chemist. So let's look here at 2 routes for the synthesis of 2-phenylethanol. Okay? 2 routes that'll get you to the same place. Okay? Which one are we going to choose? Okay? Well, the route that's up top is preferred because it has fewer steps. It avoids needing an excess of benzene, which we would have to have down here in the alkylation reaction. And it doesn't have any radical reaction. Right? Radical reaction is the step down here. Right? When we have a radical reaction, remember it's a game of probability, so we're going to get a bunch of side products. Right, so down here, we've got 1, 2, 3, really 5 steps, because the hydroboration oxidation here is 2 individual steps, versus 1, 2, 3, 4, 5. Hydrolysis, simple. You're not going to lose any appreciable yield. That's 2 steps. Those are going to get a high yield. We talked about that in chapter 11 with the copper couplings. Right? But overall, you're going to get a much higher yield here. So 2 routes to get to the same product. And now you've learned enough reactions, chances are for anything, you can get there multiple ways, but we want to go there in as few steps as possible, avoiding things like excess reagents, especially if they're carcinogenic, avoiding radical reactions when you can. So let's look at the second example here. This illustrates the fact that the order of reactions is important with benzene, okay? Because it depends what I'm trying to make. If I'm trying to make something that's ortho or para versus something that's meta, the steps will dictate that. If I do a sulfonation first and then a bromination, I'm only going to get the meta product, right? Because that sulfonate group is a meta director. Versus if I do the bromination first, now that's a weakly deactivating substituent, so it's an ortho para director. So I'll get a mix of 2 of those. So you have to pay attention to what kind of product you're making for the order of your steps. Same thing shown here, not necessarily for the product that you get, but sometimes there's only one order that will get you any product. Okay, if I'm trying to take benzene and put on a nitro group and an acyl group there, I have to do the acylation first, the Friedel-Crafts, and then the nitration. Okay? Because we just mentioned a couple minutes ago, if I do the nitration first, then I have a meta director, and that can't undergo Friedel-Crafts reaction. So that's the only way to get this product. You couldn't get it any other way, not with the reactions we have anyway. Okay. What about over here? Okay. Do I do a chlorination and then an oxidation, or do I do an oxidation and then a chlorination? Okay. Well, again, we see the order of the reactions is important. Do I get a meta group or do I get a para group? Right? And when you oxidize the alkyl substituent can change the reaction if that's not your finished product. Right? We see in this step here, right? The first alkyl group, right, we put on by a Friedel-Crafts reaction, but then if I wanted to add another alkyl group, right, I can't do that if I have a meta director, so I have to do the second alkyl group by a coupling reaction from chapter 11. So there's a whole bunch of considerations to look for, right? Other examples here. We have to do an acylation in this situation to avoid a carbocation rearrangement. That's the only way to get that straight chain ethyl group. And I have to do it before the sulfylation, right? Because then if I did the sulfylation first, I would have been deactivating. So that's the only way to get the para group. And I have to do the reduction here first, right? I couldn't save that to the end because then that would affect my sulfur group as well. Alternatively, right, you can do a coupling reaction as well. You see the utility of those from chapter 11. They're really useful. What about things, those were disubstituted. What about trisubstituted benzenes? If I've got 2 substituents already and I'm putting on a third, I have to think about how both groups that are already on there direct. And I have to think about sterics. Okay? Now in this one, no big deal. Right, toluene is an ortho para director, the CH3 there. Para group's already taken, so that's going to want to put them in the ortho position. Nitro group's a meta director. They want them to go to the same place, right? And that molecule, that's the product. Flip it over, it's the same in 3D. So you only get one product. Awesome. Right? But what if that's not the case? Okay. Now I've got the chloro group that's a meta director, right? But I've got this toluene here. Sorry, this chlorine is an ortho para director, getting one slide ahead of myself. Chlorine's an ortho para right here, so it wants to take up these 2 in this one. Toluene here, 1, 2, 3, also ortho para. But notice 2 major products here. Not a third one where I put it over here, because this is where I'm thinking about sterics. I want to avoid having all 3 of those groups next to one another on the ring if I can do it. It's an argument because of steric hindrance. Now getting to the one I was talking about before, right, where the things are competing. Now my phenol here, the OH, is an ortho para director. It wants to go up here. CH3, also an ortho para director. Now this is why knowing the classes of reactivity is important, right? Because the strong activator, the OH, wins over the weak activator. Okay? So it's going to go in the ortho position up here. Right? So strong beats out weak. A strong activator would beat out a weak or moderate activator. It would also beat out a weak deactivator. Now, we can also, right, in this situation, I've got an Ortho ParaDirector up here, an Ortho ParaDirector down here. They're about the same in terms of their activation, right? So in this situation, because I don't have a strong beating out a weak, then I get just a mixture of my products. So as you can see from this video, which is a little lengthy, right? The effect of the substituents is huge. How they affect the reactivity, right? Sometimes you don't even need a catalyst. Other times they won't react at all. How they affect the reactivity of benzene and their derivatives, where the substituents go. 1, 2, 3 substituents. Lots of considerations, right? Only 5 EASR reactions, but once we start to put on substituents on there, the game changes quite a bit. Okay? So that'll conclude everything from chapter 4, and then we wrap up the video, or sorry, the chapter in our final video, video 5.